Now we're going to image a different way. This is imaging of cells using a beam of electrons. This is scanning electron microscopy. It's become so commonplace now we don't even consider the wow factor of it. But these are 5 bacterial cells. They're an interesting bacteria because this bacteria are not only a target of biotechnology, but they have benefited from biotechnology over the last 30 or 40 years. How have they benefited? This is Staphylococcus Aureus. This is a bacteria that lives in a very scary place. It lives on human skin. It's one of the most common flora to live on human skin. It also lives in places like high school locker rooms, professional athletes' locker rooms as well. Staph Aureus has benefited from biotechnology in that our use of antibiotics over the last 60, 70 years has put evolutionary pressure on Staph Aureus and other bacteria. And what Staph has done, it's managed to develop resistant forms of itself to perpetuate its DNA under that evolutionary pressure. Biotechnology has actually made better Staph, but to humans, that's worse Staph. And you may have read about it or heard about it in your school or your newspaper or on TV as superbug, or what's called methicillin-resistant Staph aureus, or MRSA. MRSA is a drug which is a bacteria that is resistant to most of our antibiotics. And if MRSA had arrived 20 years ago, we wouldn't have had any antibiotics to treat it. It is a product of our healthcare system. We use antibiotics to treat infections. Eventually, bacteria develop, under that evolutionary pressure, develop resistance mechanisms. Some of them are simple resistant mechanisms. Build a thicker wall in your cell membrane, and you can be somewhat more resistant to antibiotics. But some bacteria are very sophisticated. They'll build enzymatic pumps that will pump out the antibiotic that's trying to get into its cell. That's a pretty impressive manipulation of biology for the purpose. And in fact, Staph aureus has produced an amazing array of biotechnology products to defend itself. I'm going to talk about, and when many of you in your careers to come will hear case histories, I'm going to walk you through a case history. This is a patient in 2006. In 2006, the MRSA rate, when you showed at the ER, was about 50-50. Half the cases of skin infections it showed at an emergency room were MRSA. But in general, emergency room physicians did not recognize it as MRSA. They said, this is a standard Staph, I'll give them the standard antibiotics. This patient was 40-something years old, presented at a local ER with this gross, and only the folks in front can see how gross that is. There's this lesion behind the left knee. It's crusty, it's oozing, it's black. The patient could not identify where it started or how it started. Importantly, this patient was out in the community. They were not in the hospital. Many resistant infections occur in the hospital because that's where we use most of our antibiotics. So in fact, the evolutionary pressure in the hospital is stronger, and that's where the bacteria develop resistance. MRSA has actually gotten out into the community. It's replicated itself, ridden on skin of patients out into the community, and has survived out in the community in places like locker rooms and on patients who carry but do not show signs of infection. So this patient showed in the ER on a Saturday with this infection, showed at another ER on a Monday. By Tuesday, had to be hospitalized. After 4 days, was hospitalized. This is low-tech biotech. This is Sharpie lines that doctors will draw around people's infections to look at the extent of the erythema, the swelling and redness. That's the infection spreading. Within 4 days, this patient went from walking around, walking into the ER, to bedridden at a hospital with a surgical consult in order to save their leg. We'll take a little aside on biotechnology and get back to this patient and how they were treated. Here's biotechnology in action. This is Mount Ararat in Turkey. On the slopes of Mount Ararat in Turkey, in the soil there's an amazing biotechnology factory. And it is the soil. We get a lot of our antibiotics from soil because the bacteria in soil, they want to protect their territory. What else lives in soil? Fungus, bacteria, other bacteria. So bacteria make antibiotics, agents to kill the other bacteria in the soil. And one of those bacteria that happens to live in the soil on the slopes of Mount Ararat is Streptomyces roseosporus. affectionately called Rosie. I wish the microbiologists called her Rosie, but they don't. It's Streptomyces roseosporus. Roseosporus makes one particular molecule that had never been discovered before. It was discovered in the 1980s from this soil from Mount Ararat by scientists at Eli Lilly. They isolated that compound, found it looked like this. This is a 3D structure. It's got an amino acid head and a fatty tail. It's called daptomycin. Eli Lilly tried to develop it, found it was unsafe in humans, shelved it. The company I worked for, Cubist Pharmaceuticals, in the late 90s, said, you know what, this drug might have utility, particularly if these rates of MRSA start to rise. Took it off the shelf from Lilly, found a safe way to dose it in humans, and developed it as a drug, approved as a drug called Cubicin in 2003. And it was in fact this drug that was used to treat that leg I showed you before. How does this antibiotic work? It's kind of interesting. Here's another scanning electron micrograph of Staph Aureus. But Staph Aureus looks a little different. Look at the membrane here. See these things? We call them blebs. It's one of the not so hard to pronounce and kind of cool words scientists come up with. A bleb is a defect in a bacterial membrane. In this case, what daptomycin does is form an artificial ion channel. It doesn't disrupt the membrane. It doesn't break it up the way soap would. It forms an artificial ion channel that's exactly the right size for a potassium ion to leave the bacterial cell. When potassium leaves, potassium is positively charged, it changes the electrical potential of the cell. And the cell, it's like an on-off switch. It shuts the cell off. And it can no longer reproduce, it can no longer live, and it dies. And it was daptomycin and that mechanism of action, or purported mechanism of action, that was used to treat this patient. And within 2 days of treatment, this patient got to go home. Within a week, he was playing softball for the Cubist softball team. That, ladies and gentlemen, is my left leg. I am standing here today, literally, because of biotechnology. Remember, any one of you can be a patient. Any one of you will know a patient. Any one of your families might be patients. I am a patient. I am a product of biotechnology. I work in biotechnology, and I have benefited greatly, and my family has, from biotechnology. How did I get it? We do not know. I was just out in the community. I was on vacation. I have no clue. A lot of people, and I was one of them, claimed, I bet you it was a spider bite. But spiders get a bad rap. Everyone thinks it's a spider bite. If you actually see an actual spider bite, it looks nothing like that. It could have been, for example, if staph is living on your skin, and you just get a break in the skin. Your skin is a powerful tool to protect you. So it could have been, for example, a mosquito bite that I scratched. I broke the skin, there happened to be staph around, and it got in. What I've been lucky about is that I've never gotten a recurrent infection, because some people end up colonizers, where the MRSA actually lives on their skin for their whole lives. And anytime they get a cut, they're at risk of getting a MRSA infection. A side note to that particular story, a scientist I worked with who actually helped discover daptomycin, just a month after my infection, got his own staph infection. He got it from, we think, from a shot he received into his arm, which likely pushed the bacteria from his skin into his bloodstream. A bloodstream infection is a very difficult thing to treat. He, in fact, fought for about a month and a half and ended up dying from his bloodstream infection. This is a gentleman who actually discovered 3 antibiotics, 2 of which I was treated with. He saved my life, yet a month and a half later he succumbed to bacterial infection.